Now we are going to see some properties of modulus of a complex number. Now recall that modulus of a complex number can be defined in the following way. This is z, which is a complex number, coordinates xy. Then we can associate the following vector with this complex number. Here x is basically this length and y is basically this length, because if I want to reach this point, then I have to travel x units along real axis and y units along imaginary axis. So this length is basically x and this length is basically y. Now this x is also the real part of this complex number z, and this y is imaginary part of this complex number z. And this length, the length of this hypotenuse, is basically the modulus of this complex number. Now we know that from elementary geometry that the length of the base is always less than or equal to the hypotenuse. So we can say that length of the base, real part of z, so since it is length, so we denote this mod. So this is going to be less than or equal to the hypotenuse of this triangle. Now we also know that since real part of z is a real number, and we know from real numbers that a real number is less than or equal to its absolute value, so we can say that real part of z is less than or equal to mod of real part of z, which is less than or equal to modulus of z. And similarly, we can say the same statement about y. So y is basically imaginary part of y, so we can say that imaginary part of z is less than or equal to absolute value of the imaginary part of z, and since perpendicular of a triangle is less than or equal to hypotenuse, so we can say that this is less than or equal to the modulus of z. And we also know from Pythagoras theorem that for a right angle triangle, so we can observe that it's a right angle triangle since this one angle is 90 degrees. So for right angle triangle, Pythagoras theorem says that square of the length of hypotenuse is equal to sum of the squares of base and perpendicular. So in this case we have z modulus square is equal to x square plus y square, or in other words, real part of z square plus imaginary part of z square. Now the next property about modulus is the well-known triangle inequality. So this inequality says that if I add two complex numbers, then the modulus of this complex number z1 plus z2 is bounded above, or it has an upper bound, mod of z1 plus mod of z2. So if z1 is this complex number in plane with coordinates x1, y1, and z2 is this complex number in plane with coordinates x2, y2, and we can also associate vectors with these two complex numbers, then the addition of these two complex numbers can be represented geometrically as the diagonal of this parallelogram, so which is z1 plus z2. Now this inequality says that the length of this diagonal is less than or equal to the sum of the lengths of z2 and z1. Okay, and we can also see that there is equality here. So this length will be equal to the sum of these two modulus when z1 and z2 are collinear. Now the next property provides us a lower bound on the modulus of the addition of two complex numbers. Now using triangle inequality, we can prove this inequality in a very simple way. Now, if I start from the modulus of z1, I can write it down as z1 plus z2 minus z2. So if I cancel these two, then I'll be getting the same thing. Now using triangle inequality, we can say that this is equal to z1 plus z2 modulus plus the mod of minus Z2. Now it's a very simple exercise to see that if I calculate modulus of a complex number and if I calculate the modulus of minus of this complex number, then they are the same. Now this implies that Z1 mod minus Z2 mod is less than or equal to Z1 plus Z2. Now if I interchange Z1 and Z2, so interchanging Z1 and Z2, I have another inequality which is mod of Z2 minus mod of Z1 is less than or equal to modulus of Z1 plus Z2. Now I can write it down as minus of modulus of Z1 minus modulus of Z2, which is less than or equal to Z1 plus Z2. If I multiply both sides with minus, then I'll be getting Z1 mod minus Z2 mod is greater than or equal to, since when we multiply with negative sign, the sign of the inequality changes. So greater than or equal to minus modulus of Z1 plus Z2. Now using this inequality 1 and this inequality 2, we can observe that mod of Z1 minus mod of Z2 is less than or equal to modulus of Z1 plus Z2 and is greater than or equal to minus modulus of Z1 plus Z2. So which implies this inequality, since we know that for real numbers, if I have alpha a real number, this is origin and minus alpha is this one, and if I say that this x is less than alpha and greater than minus alpha, then all these real numbers which satisfy this condition are basically these real numbers. Okay, so the mod of x is less than alpha. So that's why this third inequality implies directly this inequality. So now we have an upper bound and lower bound for the modulus of addition of two complex numbers. On the same line, we can prove the following inequality. If I have Z1 minus Z2, then the subtraction of these two complex numbers also has the same upper bound, the modulus of Z1 plus modulus of Z2 greater than or equal to the difference of the modulus of Z1 and Z2. Now consider a complex number such that the modulus of Z is equal to 1. So what are these complex numbers? So consider this complex plane, and we also know that what is the modulus of a complex number? It is basically distance from origin to that point. So in other words, we are looking for those complex numbers in the complex plane whose distance from the origin is exactly equal to 1. So set of all points whose distance from origin is equal to 1 is of course a circle of radius 1. Now if I want to calculate an upper and lower bound for Z minus 2 modulus, then using these inequalities we can easily calculate that. And what is going to be the upper bound? So Z minus 2 is less than or equal to, modulus of Z minus 2 is less than or equal to modulus of Z plus modulus of minus 2, which is the same as 2, which is equal to, since modulus of Z is 1, so this is equal to 1 plus 2, which is equal to 3. So the modulus of this complex number Z minus 2 is always less than or equal to 3. And similarly, using this part of the inequality, we can calculate the lower bound of this thing. So Z minus 2 mod is greater than or equal to mod of Z minus mod of 2, so which is equal to mod of 1 minus 2, which is equal to 1. So this complex number Z minus 2 is less than or equal to 3, and the modulus of this complex number Z minus 2 is greater than or equal to 1. So this is the lower bound of this modulus of this complex number, and this is the upper bound of the modulus of this complex number. Now we have seen some properties of modulus, especially we have calculated upper and lower bound for the modulus of the addition of two complex numbers.